Okay, make based on the fitting parameters and the goodness of fit value, you can then make a decision which one you would like to take as being the proper distribution for your data set. A lot of the testing we do later on assumes that your data is normally distributed. So if it's not normally distributed, you can transform your data set so that it's normally distributed by doing a mathematical transformation. And so it's something that to consider, to go from something which is log normally distributed to normally distributed. You do the transformation. And then you can use the hypothesis testing for your data sets. So when you would come up with your data being raw data being, for instance, log normally distributed, then it makes sense for you to make this transformation so that it's normally distributed, and then do the hypothesis testing. So that's the sensible thing to do. Okay. Sometimes people say, hey, my data set is log normally distributed, but then just use their raw data set to do the hypothesis testing, t-testing for instance, and that only works if you have a normally distributed data set. Okay, so probability plotting is something we will do fairly often. It's also something which is useful when we're looking at the effects in a design, the results of a designed experiment, and we're comparing effects. So the effects are the, you could say, the size or the impact of a particular factor on your result. And so if you have a large effect as compared to a small effect, you want to be able to say, yes, this large effect is meaningful, the small effect is a random effect. And so effects can also then have a normal distribution, and you can make then a distinction between something which is just due to the errors in your design, or in your measurements rather, and something which is really of significance to the system, which is really there. By plotting it, I'm running way ahead of schedule here, but I'm just indicating that we'll also use this probability plotting when we're looking at the results of the design of experiments. So it's good to do plotting, probability plotting, and also on the exam. Often it's quite useful to do that, so it's good to have, so you can bring actually probability paper to the exam. Sometimes I forget to mention this, and people are doing this then by hand, but if you want to make yourself a more easy probability plotting, you can just bring the probability paper. So how can you then do this when you have normal, you want to check if your data set is normally distributed by using this probability plot paper. So you basically rank, so this is your data set, okay? This is what you've measured for the random variable, and you then rank them, okay? And then by ranking them and transforming this to this here, j minus 0.5 divided by 10, 10 being the data points, the number of data points you have, so the size of your sample, so to speak. You get these values, and so this you then plot. This is given in percentages here. So if you do this times 100, you can then just plot this out on the paper. if it's normally distributed, this should give you more or less a straight line. Okay, so that's how it goes. So you have this 0.05, so that's 5%, so this 176 data points should be here at 5, which is almost 5. I don't know why this is not exactly 5. Okay, and that should be 95. Okay, so this is the way you can do it, and then the question is this now normally distributed? You can do this with some type of fit. Yeah?
Sorry, the Shapiro-Wilk test?
Huh?
Or the Smirnov-Komarov test?
You can do all of these tests, yeah, but there's also what is called a pencil test. So you put your pencil over the line, and if it covers the data points, that is also okay. All right. Yeah, actually, when we'll do this for the effects, when we're analyzing our results for the design of experiments, an effect which is significant will be outside of the normal distribution, and so that will stick out like a sore thumb. Okay, so it will just be way off that line, and then you can say, okay, this is a significant effect. Okay. If you don't have this normal probability paper, you have to then translate this into the z value through the tables, and then you can also plot it as z and not the p. And it's the same, but you have to then go back to the tables and transform that. So that's a bit more work. So easier is to just bring the normal probability paper. Okay, so if we're looking at an example here, crack length for an aluminium alloy, and you have some measurements of crack length, you can then put this into a graph like this, normal probability plot, and to see if this works out. So this is a normal probability plot. This is log normal, and this is a Weibull plot. So in this case, it looks like the log normal is maybe the better choice. If you have something which is by definition a positive number, you could kind of already assume that the normal probability plot will not be so good. Just one tip for your report as well. Sometimes it happens, not everybody does it, but some people just have their complete data set of the design of experiments and put this in the normal probability plot. If you have, when you're setting your experimental conditions, if you have factors which have a significant effect on the result, that should not then lead to something which is normally distributed. Okay, so almost by definition, if you have a sensible experimental setup, that should lead to something which is not normally distributed, because you have things in your, you have factors in your experiment which lead to non-random errors, so to speak, because you have a change in the temperature, and yes, suddenly the reaction rate goes up, for instance. Okay, so if you are playing with reaction rate, with temperatures and concentrations, that will change your response variable in a systematic way, and so you will get something which is normally distributed. So the way to check for normal distribution is, of course, to have one setting, one temperature, concentration, and so on, the factors fixed, and then do a bunch of repetitions, okay, for the same condition. All right. Sounds slightly absurd, but it happens every year 2 or 3 times that there is a report where they do check their distribution based on their complete data set for the design of experiments. Okay, so this year it will not happen because I told you to not do this. Right? Do you understand why?
I'm sorry, I don't understand. So our errors shouldn't approach a normal distribution?
No, okay. Yes, I'm kind of jumping all over the place. I'm sorry. So it's, my empathic level was too low. But so when you do the project, at a certain moment you'll do a design of experiments. Okay, this means that you will have your 4 factors, and you will change your factors so that you have different runs. Okay. So when you take that data set, there will be notable differences between your response variable values. Okay. Now, say you've done it's 2 to the 4, which is 16, and you do 2 replicas. You have 32 data points. Okay, and now you put this in a normal probability. That doesn't make much sense. Okay, because you will have things which are going all over the place. Okay, and that happens sometimes. So this year it will not happen, thanks to your question, because now it's clear to everybody what I was saying. Yeah? So good. The bad thing is, last year I also said this. It still happened, but I didn't have you in the class. So now it's going to be okay. So thank you for that. So yes, so we can do these probability plots. How are we on time? So we can now go to discrete random variables. So I will stop here so you have time to go to your next class. I have already people waiting who want to enter this classroom.